So, this is modern physics lecture number 9, and welcome to the class. What we were discussing in the previous lecture? Any idea?
Binding energy, sir.
We were discussing binding energy. Great, binding energy of the nucleus. And what is binding energy of the nucleus? Can you let me know what you remember about binding energy? What was the binding energy of the nucleus?
The energy required to split
The energy required to
it nucleons.
nucleus into its constituent material constituents, which
Yes,
is the
sir.
nucleus, which is the number of protons and number of neutrons. We also had seen something known as the mass defect. Do you remember what is mass defect? Mass defect of a nucleus.
Yes, sir.
What is the mass defect of a nucleus? How do you find out the mass defect of the nucleus? Delta M, we call it. Mass defect of the nucleus. From where this comes? Tell me.
ZMP plus A minus Z.
No. You are telling me the formula. You tell me what is mass defect. From where this mass?
Nucleus is less than the nucleons.
Yes, the total mass of the nucleus is less than the mass of the nucleus. Total mass of the nucleus. The difference in the mass is known as the mass defect. So it will be delta M will be equal to total mass of nucleon. If you can write it like this, total mass of nucleons. Nucleons means
protons
plus neutrons minus what?
Mass of the nucleus.
Minus the total mass of the nucleus. This is what I call, or we call, as the mass defect. Now, if I write it in terms of formula, how does the formula look like?
ZMP.
Z, that is the number of protons multiplied by the mass of the proton. Yes or no?
Yes, sir.
Plus
A minus Z.
A minus Z, which is the number of neutrons multiplied by the mass of the neutron. This has to be added up because this consists of the total mass of the nucleus. Yes, minus
mass of nucleus M.
Mass of the nucleus, I write it as Mn, mass of the nucleus. We understand this?
Yes, sir.
That's it. We also saw one more formula where instead of mass of the nucleus, instead of the mass of the nucleus, we had the mass of the atom. Since the mass of the atom also has electrons in it, therefore, if I use mass of atoms on the left hand side, on the right hand side, I will have to add the mass of the electrons on the left hand side. Do we understand this?
Yes, sir.
So instead of, if I have mass of, if here I have mass of the atom Ma, if I have the mass of atom Ma, here I will add mass of the electrons Me. Do we understand this?
Yes, sir.
Great. This is the mass defect. Mass of the nucleus is less than the mass of the total nucleons. Now, because of this difference in mass, there will be some energy which is required to break the nucleus into its constituents, and that energy is known as
binding energy.
That energy is known as the binding energy. Binding energy. We denote it by delta E. Binding energy, delta E, and delta E is this mass defect multiplied by c square, where c is the speed of light, Einstein's equation. We understand this, right?
Yes, sir.
And if I just write it in terms of mega electron volt, so what do? I write the mass defect in terms of AMU, and I multiply it by 931, and the answer would be in mega electron volts. We understand this?
Yes, sir.
Well done. This was what we discussed in the previous class, which we would be using in today's class. And now we come to the next topic. Now, what we understand from here, that every nucleus will require some energy to break it into its constituents. Yes or no?
Yes, sir.
So we might understand that if you require more energy to break the nucleus, that means the binding energy will be more. And if the binding energy is more, we can understand that the nucleus is going to be more stable. Yes or no?
Sir.
But that is not the case. The only thing that decides how stable is the nucleus is not the binding energy, but it is something else that decides how stable is the nucleus. And this thing we have already discussed previously, which I said that I will be coming back. And the factor that decides whether the nucleus is stable or not is not binding energy, but it is binding energy per nucleon. Do we understand this?
Yes, sir.
So the factor that decides how stable is the nucleus, how stable the nucleus is not only, it's not basically binding energy, it is binding energy divided by the number of nucleons. Whosoever has this ratio more, that will have more stability. As you can see, it is written over here. It is more important than binding energy. Obviously, it is also binding energy, but it is binding energy per nucleon. This is more important than binding energy because this value decides the stability of a nucleus. How stable is the nucleus? And how do you get this binding energy? It is found by dividing the total binding energy by the mass number. When I say mass number, that means the total number of nucleons. Do we understand this?
Yes, sir.
Please note this down. You will have to note this thing down. Because once you note it down, we shall move to this thing. I hope you are noting it down, bacha. The factor that decides the stability of the nucleus is not binding energy, but it is binding energy divided by the number of nucleons, or we call it binding energy per nucleon. Have you noted it down?
Yes, sir.
And then comes this table. Do you remember this table?
Yes, sir.
We discussed this table previously, and as you can see on the yellow axis, on the y-axis, I have binding energy per nucleon. Everyone sees this, yes or no?
Yes, sir.
So I have binding energy per nucleon here, and I have the mass number here. Everyone sees this, correct? We see this table, yes or no?
Yes, sir.
And as you can see now very clearly, when the mass number is very low, the binding energy per nucleon is very less. Yes or no?
Yes, sir.
That means smaller nuclei are not very stable. Do we understand this?
Yes, sir.
Two hydrogen atoms, the nucleus of the two hydrogen atoms, they are not very stable. If they are not very stable, then what will they do? If they are not stable, what will they do? If given a chance, they will combine together and become a heavier nucleus, because when they get heavier, when the mass number becomes more, the stability increases because binding energy per nucleon increases. Yes or no?
Yes, sir.
That process where two smaller nuclei combine together to form a bigger nuclei, that process is known as
Fusion.
nuclear fusion. And this is what provides energy to the sun, hydrogen becoming helium, helium becoming higher element. The only problem with this fusion is it requires very, very high temperature. If we can achieve that, those high temperature, this fusion, the energy given in this fusion is not radioactive, and this is clean energy. Do we understand this?
Yes, sir.
Now, if I go in this region on the right hand side, what do I see? I see that when the mass number increases, let me use a different pen. The red pen was used there, so I'll use a different pen so that we get an idea. I will use a blue one. When I get on this side with the blue side, I see a very interesting trend that with the increase in the mass number, the stability or the binding energy per nucleon is decreasing. Do you see that?
Yes, sir.
That means as I get bigger nucleus, they become less stable. Now, if a bigger nucleus is less stable, what tendency it will have? A bigger nucleus is less stable, but a smaller nucleus is more stable. So what will happen? One nucleus will break into two smaller nuclei. Do you understand this? Do we understand this? As mass number increases, binding energy decreases per nucleon, and hence heavier nucleus become less and less stable. If they become less and less stable and everyone wants stability, heavier nucleus will break up into daughter nuclei. So this is known as the mother nucleus, and these two are daughter nuclei. We understand this, yes or no? The audio has gone. This process is known as nuclear fission. Can you raise your hands and let me know that you understand me? Everyone. So we have nuclear fusion, we have nuclear fission. There is one particular nucleus which is the most stable of them all. Mirror, mirror on the wall. Who is the fairest of them all? Mirror, mirror, no. Table, table on the screen. Who is the most stable nucleus? Which one is the most stable nucleus? And as you can see on the top of the peak, there is one nucleus which is the most stable one, and that is iron Fe 56 26. 26 is obviously the atomic number, 56 is the mass number. This is the most stable nuclei that we have found in the universe, in the entire periodic table. What we know, there might be other elements which we'll discover with time, but this is probably going to be the most stable nuclei that we will find. Do we understand this? The most stable nuclei is iron 5626, and it has a binding energy per nucleon of 8.8. Do we understand this? I hope you have noted this down, and I will move ahead. I hope you have noted this down so that there is no confusion. Everyone understands this? Then these are the 2 points that you understand. We have already discussed them. The greater the binding energy per nucleon, the more stable is the nucleus. I have discussed this. It is maximum for iron 5626, which is 8.8 mega electron volt per nucleon, and this is the more stable nucleus. Do we understand this, everyone?
Yes, sir.
Then what else do we understand from this table? Again, these are information, and there could be a straightforward question coming from this information for uranium 235 to 38. The binding energy per nucleon is around 8.8, is around 7.7, and therefore it is not stable. Therefore, it is unstable. Do we understand this?
Yes, sir.
Then the medium-sized nuclei, which is in the middle of that iron ke aspas wale, are more stable than the lighter ones or the heavier one. Whosoever is near to that iron wala point, they are the more stable ones. On the left hand side, again unstable. On the right hand side, again unstable. Simple things that you have to remember about this table. I hope we have understood this. Yes or no?
Yes, sir.
Shall I move आगे, sir? Shall I move ahead, sir?
Yes, sir.
Okay. So now we understand that lighter nuclei, smaller nuclei will combine together to form heavier nuclei, fusion. Heavier nuclei will split into daughter smaller nuclei to become more stable, that is known as nuclear fission. We will be dealing with those two separately. The first one is nuclear fission, and it was done by Hahn and Strassman in the year 1938. And what did they do? You just have to remember the equation. They bombarded a heavier nucleus whose mass number was more than 230. I hope you understand. Bigger the nucleus, more unstable it is. This is the nucleus that they bombarded with a particle. What they get is an excited nucleus in an excited state, and this nucleus in a excited state gave rise to B, one daughter, C, another daughter, and Q, energy was released. Enormous amount of energy was released because heavier nucleus, unstable one, breaks into daughter nuclei. This is known as nuclear fission. Do we understand this?
Yes, sir.
Can you note this down, bacha? Simple equation. A is the mother. P is a particle which I am hitting it with. It could be anything. What is going to be? Let us see. Then I will have an excited nucleus in a higher state, and then it will break up into two daughters or three daughters, or depending on how many daughters. And we'll have Q, which is a large amount of energy released. Have you noted this down?
Yes, sir.
Okay. Then I have seen many questions coming from this nuclear fission, which are straightforward ones, and the entire will be in the small paragraph that we are going to discuss now. This was a reaction that Hahn and Strassman did for the first fission. This was a fission of uranium U-235. Do we understand uranium U-235? You must have heard about U-235. Yes or no?
Sir.
So they bombarded uranium U-235. You can see this here. And the particle that they used was what? Do you see the particle? The particle they used was? Oops. Don't see it? I'll make it bigger. I hope you can see it now. Do you see this reaction, bacha? They bombarded uranium U-235 with one nucleus. Nucleus?
Neutron.
One neutron. Yes, now you're getting it. Atomic number is 0, mass number is 1, and it gave, what is Ba? I don't know Ba. What is Ba?
Barium.
Okay, barium Kr. Whatever is Kr. Then I have 3 more neutrons coming out, and with tremendous amount of energy, 200 mega electron volts in one reaction. It could give Xe. I don't know what is Xe. It could give Sr and 2 neutrons again with a release of 200 mega electron volts of energy. These are the two reactions that you must remember and not forget it, because there could be a question straightforward coming from this. And I have seen questions, bacha. That is why I am telling you to remember these two equations and memorize them. Do we understand this?
Sir.
These two equations, I hope you have noted it down. These are just two examples of the equation. Many more equations are possible. Many such equations are possible. They found out the average number of secondary neutron. What do you mean by secondary neutron? These neutrons that are produced by the reaction, these are known as secondary neutrons. So one neutron, I bombarded it with boom, but the end result after the reaction, I am getting 2, sometimes 3. The average value is 2.5. There are many reactions which are possible. Now these 2 neutrons or 3 neutrons, cannot be 2.5 neutrons, can be used to bombard other uranium U-235, and that is how you get a chain reaction. Do you understand the chain reaction? That is how you get the chain reaction, and an uncontrolled chain reaction gives rise to a nuclear bomb. Do we understand this? Are we there, bacha, with me? Okay. So that is how uncontrolled chain reaction will come to chain reaction. But one neutron, we are bombarding it on uranium, and I have 2 or 3 neutrons depending on the case. Now remember this word, liquid drop model. This nuclear fission can also be explained by something known as a liquid drop model. You may not have to understand what is the liquid drop model. You just have to remember the name, liquid drop model. Do we understand this? I'll give you a minute to note it down. Liquid drop model. The mass defect is about 0.1%. You may not remember this. 93% of energy is in the form of kinetic energy of products, and 7% is in the form of gamma rays. Again, this is an information. It can come as a direct value. It may come as a direct. It may not come as a direct value. They might not ask you the percentage. They might ask you which energy is more when this nuclear fission happens. Option 1, kinetic energy of product. Option 2, the energy of gamma rays. Option 3, both are equal. Option 4, it depends on the circumstance. So the right option is that the most energy will go in the form of kinetic energy of product. Do we understand this? This is how questions are made, and this is how you answer those questions which are based on what you know. Do we understand this, bacha?
Yes, sir.
Right, sir? Then, sir, next heading, sir, you just have to read this, is a nuclear chain reaction. And a nuclear chain reaction is very simple. We have already seen it. I will bombard what? I will bombard uranium U-235 with 1 neutron. At the end, I will get some product, and we will get 3 neutrons which are produced. Yes or no?
Yes, sir.
Now, these 3 secondary neutrons can cause the fission of 3 more U-235, and I will have 9 neutrons, and 9 ke baad 27, and all this. I will have a large number of neutrons which can cause the fission of large number of U-235. This is how a nuclear chain reaction will start, and if you don't control it, you get what? If there is no control, then in a very short time, a very high amount of energy is released, and that becomes your atom bomb. Will you remember this? Will you remember this, bacha?
Sir.
Yes, sir. And that is the problem with nuclear energy, sir. If you can't control it, if the control goes away, then you have a blast, whether it's in Chernobyl, whether it's in Chernobyl, I remember, I don't remember other names, but there have been nuclear blasts in nuclear reactors. These nuclear reactors are doing this chain reaction in a controlled manner. We'll also see this controlled manner in a nuclear reactor. But if that control goes away, if something goes wrong, large amount of energy is released, and we have disaster. And that is why they are not using nuclear reactors, and they are stopping nuclear reactors. So Western companies are stopping nuclear reactors, and in India we are making nuclear reactors. We are some way behind those. Do we understand this? Have you noted this down, bacha? I'll give you a minute to note it down. Have you noted it down, bacha? Can I have some raised hand? Okay. Then again, important point, and I've seen question of coming on this critical size. Critical size. What is this critical size? Now, when this nuclear reaction is happening, one nuclear reaction of one neutron is producing 3 neutrons. But some neutrons are lost. Some neutrons are always lost. Now, when some neutrons are lost, and how are they lost? I'll just show you how are they lost. They are lost from the system, or they are lost because of neutrons getting absorbed and no fission happening. So some neutrons are lost. Since some neutrons are lost, the number of these lost neutrons should be much smaller than the number of neutrons which are produced. Therefore, in whatever fission is happening, the size of this block of uranium where this nuclear fission is happening should be equal to or greater than a certain minimum size. Because if the size is very less, you will not have fission happening because we'll be losing a lot of neutrons. This size is known as the critical size. If the uranium block is less than this critical size, we will not have any nuclear fission reaction happening. Do we understand this? Can you note this down? Critical size. I've seen question coming on this critical size, and that is why we are doing this. Two types of questions I have seen. One is on critical size, and related to critical size, we have something known as the reproduction factor. So those two things are closely related to each other. Have you noted this down? Critical size, bacha? Raise hands will give me more confidence. I think the voice has left us. Okay. Shall we move ahead? Then we have something known as the reproduction factor. You also have it in your notes. You can also see it here. You must remember this. What is this reproduction factor? It is the rate of production of neutrons, at what rate the neutrons are produced, divided by the rate of loss of neutrons, at what rate the neutrons are lost. Rate of production of neutrons divided by the rate of loss of neutrons. Obviously, if the size of the uranium is critical, exactly critical, we say that the nuclear reaction is critical. The value of K is 1. Whatever neutrons are lost, the same number of neutrons are produced. Then the chain reaction will be steady or sustained. This is what we need for the successful running of a nuclear plant. critical size, critical size, critical size. It should not be more than critical. Atom bomb will happen. If it is less than critical, well, the nuclear reaction will not happen. If the size of uranium is supercritical, and supercritical, K will be greater than 1, and the chain reaction will accelerate, and you will have an atom bomb being produced in the nuclear reactor. If the size of the uranium is subcritical, nothing happens. The chain reaction will retard and will stop. Do we understand this? So how important is this critical size? We need critical size of uranium U-235. Then only we'll have a nuclear reactor. Else we have either an atom bomb or you have a failed nuclear reactor.
Sir.
Got this, bacha?
Sir, explain critical size, sir. We didn't
It is the
understand.
minimum size that is required to carry on a nuclear reaction. If the size is less than that, nuclear reaction will stop. The size is more than that, nuclear reaction will accelerate and you will have an atom bomb. Got it?
Yes, sir.
If the size is
Reproduction
critical,
factor.
if the size is critical, you will have a very good nuclear reaction and you will have a safe nuclear reaction. That is what we need in a nuclear reactor, a safe nuclear reaction. Do you understand this now?
Yes, sir. If it is greater, it become atom bomb.
If it is greater, it becomes an atom bomb. If it is less, the
It will
nuclear
not
reaction
work.
will stop. It will stop. It will be a failed experiment. Do we understand this?
Yes, sir. Reproduction factor, sir. Explain reproduction.
Yes. So that's it. You might have seen this series, Rocket Boys, and in that series you saw that a nuclear reactor was made and it turned out blue. When it was turning out blue, that was the stage where it got critical and it was producing energy. We got this? Yes or no?
Yes, sir.
Okay. Please note it down and we'll move ahead. Noted this down?
1 minute, sir.
Okay, sir. Remember this critical size and this reproduction factor, you just have to remember them. If you understand any one of these, the other one automatically comes. Yes or no?
Yes, sir.
K is 1, size is critical, nuclear reactor. K is greater than 1, atom bomb. K is less than 1, field
It will
experiment.
stop.
Yes, field
Completed,
experiment.
sir.
Okay, sir. Then we have nuclear reactor. No one will be asking you to draw this nuclear reactor, but they can ask you question based on that. What are the fuel used? Uranium U-235 and Pu. I don't know what is Pu. What is Pu? 239. Pu-239 is the best. Why it is the best? Information based question. Must know this. Its critical size is less than the critical size of U-235. So I can have a smaller block of Pu. What is Pu? Plutonium. Pu-239. I can have a smaller block because the critical size is less, but it is not naturally available. Do we understand this?
Yes, sir.
Then I have,
It is artificial, sir. PU.
yes,
Okay.
moderator. When this nuclear, you just have to understand the function. There can be a question based on the function. And what is the moderator out? What is the use of the moderator and which moderator is used? The function of the moderator is to slow down the fast neutrons. As I told you, 93% of the energy is in the form of kinetic energy. These neutrons are going to be very fast. You have to slow them down. And how to slow them down? By using moderator. Heavy water, D2O, is used as a moderator. You can also use graphite as a moderator. Neutrons will get slowed down, and that is the function of a moderator. The moderator should be light and it should not absorb the neutrons. Its only purpose is to slow down the neutrons, and that is done by heavy water or graphite. We understand this? Please note this down. Moderator, what is the use? One line. What is the moderator? Second line. What it should do, what it should not do. We got this, bacha? We noted this down. The function of the moderator. And also, who created this nuclear reactor? Enrico Fermi. That's the first line. I forgot to mention that. I've seen questions that straight away ask you the name of the scientist who created the first nuclear reactor, Enrico Fermi. Have you done this?
Sir.
Information-based question, straight questions. If you know it, you know it. You don't know it, you don't know it. Next one is the other two things, most important ones. Everything in the nuclear reactor is an important one. We're only talking about the broad parts of a nuclear reactor. A nuclear reactor is a very complex machine. We can't get into the details of it. We can only see the broad parts. And one of those broader parts is the control rods. And as the name suggests, what will be the function of a control rod? It is going to control the nuclear reaction. That means it will capture the slow moving neutrons and it will control the chain reaction. It is going to absorb that neutron. For every nuclear reaction, we'll have 3 neutrons. Yes or no?
Yes, sir.
But I only need 1 neutron because other 2 are going to create the atom bomb. So I need to absorb these 2 extra ones. I only need 1. So who is going to do the process of absorbing? These are the control rods. Boron and cadmium are the best absorbers of neutron. Do we understand this?
Sir.
Then I have the coolant to cool down everything because a large amount of heat is produced and it is transferred to water. Do we understand this?
Yes, sir.
Large amount of heat is produced. You can heat water, you can convert it into steam, and then you can use that steam for other job as well. So nuclear reactor also produces steam, heat. If you can do it correctly, well done. If you can't do it correctly, well, an atom bomb, you are creating an atom bomb in a nuclear reactor. Do we understand this?
Sir.
Okay, bacha. That's about the nuclear reactor. I hope you have noted this down. I'll give you a minute to note it down. You got this? Shall I move ahead, bacha?
Sir, how heat is transferred into water?
You just heat up water.
Sir?
You just heat up water. There are many ways you can heat up water. Right?
Okay.
Okay, shall we move ahead, bacha?
Completed, sir.
Then there's something known as the fast breeder reactors. Again, I've seen questions coming on this, and that is why I'm going to do this. In short, what is a fast breeder reactor? You start with uranium U-235 to continue the process. But in the process, if you get plutonium Pu-239, then this reactor, it produces its own fuel. Plutonium 239 is also fission ready. It's also nuclear fuel. It's not readily available. It's not naturally available. You produce it. It's produced in a nuclear reactor only by the fission of U-235. Those reactors are known as fast breeder reactors. So once you have U-235, you will produce 239 plutonium.
Sir.
And you will have more fuel. You produce your own fuel. How does it produce? U-235 gets converted into 238, then into 239, and this 239 converts into plutonium 239 after 2 beta decay. This plutonium 239 can be separated, taken out. New fuel has come. We take it out, store it, save it. Its half-life is 2400 years, so it will stay for a very long time. Do we understand this?
Yes, sir.
These reactors where plutonium is produced, not naturally available, are known as fast breeder reactors. Yes or no? We understand this. Obviously, I'm not making you a nuclear scientist over here, but these are the questions that I have seen, and that is why I am doing this. I hope you have noted this down.
Yes, sir.
Yes, sir. Then, sir, looking at the reaction, sir, this is the reaction that gives us plutonium, best fuel of fission. This is how I get uranium U-238 converts into 239, and uranium 239 by beta emission, 2 negative beta emission gets converted into plutonium, which is the best product or the best fuel for nuclear reaction. And in Hollywood movies, you must have seen every time there is a nuclear weapon, it is created in Russia and it is used to bomb United States of America, and always they call about plutonium, 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 plutonium core, plutonium this, plutonium that. We got this, yes or no?
Yes, sir.
That plutonium, small plutonium, and you have nuclear weapon. Uranium, you need big block. Plutonium, you need small block, transportable. That's why plutonium, America, Hollywood, nuclear weapon, nuclear bomb, this, that, what, that. Everything is coming from this. So they have read nuclear physics. And that is how they are creating all those wonderful Hollywood movies. Do we understand this, bacha?
Yes, sir.
Yes, sir. No, sir. Then, sir, what's fission is done? What would be the next heading, my dear friends?
Fusion.
Fusion. Are we ready for fusion? We are broken.
Combining.
Yes, we have broken hearts. Now we are going to
Adding them.
combine hearts, and that is the best thing. Don't break hearts. Don't break heavier nucleus. Combine smaller ones.
Yes, sir.
That is not uncontrolled. You will not have an atom bomb getting created. You will have fresh and clean energy coming. Nuclear fusion is the next heading, and there comes nuclear fusion. It is a phenomenon of fusing two or more lighter nuclei to form a single heavy nuclei. Do we understand this?
Sir.
A plus B are my daughters, and C is my mother. So two daughters getting birth to a mother. We can't call it daughter mother because daughter cannot give birth to a mother. It's always mother to daughter. So two lighter nuclei A plus B give you C, which is heavier, but it is heavier, but it is more stable. Do we understand this?
Yes, sir.
And then you have this Q. This Q is the energy released in the fusion. The product C is more stable than the reactants A and B. Do we understand this?
Yes, sir.
The mass of the nucleus C is less than the mass of A plus B. Do we understand this?
Yes, sir.
The mass defect will be mass of A plus mass of B minus mass of C. Do we understand this? The energy release will be mass defect multiplied by 931 mega electron volt. Do we understand this?
Yes, sir.
The total binding energy or the change in binding energy of the bigger nuclei, because it is more stable, will be more than the combined binding energy of the two. Do we understand this? Yes or no?
Yes, sir.
Then, sir, please, sir, note it down, sir. Most important thing about nuclear fusion, sir. Please note it down. Everything has to be noted down. You cannot just mark it in the sheet because you will forget it. Nuclear fusion is what Have we noted this down, bacha?
Yes, sir. Completed.
Well done, sir. You have been very quick, sir. I hope you are noting it down, sir, and you are not just marking it in your books. You are noting it down with your own hands, yes?
Yes, sir.
In the notebook, yes? Okay, that's good. That's the spread I need. And then comes what? A simple nuclear fusion reaction. As you can see, this is just an example. 4 helium, 4 hydrogen becomes a helium nucleus, 2 positive beta particles, 2 neutrino, and you have 26 mega electron volts of energy being released. What you can see is energy released in nuclear fusion was 200 mega electron volts. Yes or no?
Yes, sir.
Very high. That means the energy release per reaction of nuclear fission is very high compared to energy released per reaction in a fusion. Do you understand this?
Yes, sir.
But that is not the factor that determines. Obviously, nuclear fission, we can do it very easily. Nuclear fusion is not so easy. What also matters is the energy release per nucleon. For one nucleon, how much energy is released? That energy is very, very small, and don't look at the numbers, because numbers don't, we will not be able to understand those numbers. What we need to understand here is the energy release per nucleon in fission is very small compared to the energy release per nucleon in fusion. And these are the two things, number one and number two, you should not get confused with, because there will be a question which is going to come and you will get confused which energy are they talking about. Per reaction, the energy in fission is very high, but per nucleon, the energy is very less. Do we understand this?
Yes, sir.
What, sir? For one reaction, if you compare the energy in one reaction, the energy in fission will be always very high. But if I compare energy release per nucleon, the energy of fission is very, very less. Do we understand this?
Yes,
These
sir.
are the two things that you must remember in your head, because this is the basic difference between what? Nuclear fission and nuclear fusion. I hope you will not forget this. Yes or no?
Yes, sir.
Now comes, how do we create nuclear fusion, and why are we not creating nuclear fusion? Well, if nuclear fusion is so good, it is not radioactive, it does not give a chain reaction, you will not have an atom bomb coming from a nuclear fusion. Why are we not able to do it? Tell me why we are not able to do it. Why we can't create all the energy from nuclear fission? Lots of hydrogen available, fuse hydrogen, water is there, lots of water, 70% of earth is water. And just yesterday I read this news that our transport minister, Mr. Gadkari, he came in a car and it was running on hydrogen. Have you seen this news?
Yes, sir.
He came in a car driven by hydrogen, clean fuel. If I have hydrogen, which is available, why don't fuse it, make helium, and have free energy? I mean, not free, and have clean energy. Why we can't do it? Why it is such a big task? Why it is such a big task? Because to have a nuclear fusion happening, two things are required. And what are those two things?
Temperature and pressure.
One is a very, very high temperature we require. It has to be happening at a very high temperature and very high pressure. The required temperature and pressure and earth are not possible, and that is a problem. You are not able to create that conditions in a lab, in a factory, in an industry. We are not able to create that much of high temperature and that much of high pressure that we can make a fusion reaction possible. Obviously, we are working on it. Probably one day we'll be able to do it. Where does this happen? It happens in the sun. Hydrogen becoming helium, helium becoming lithium, and all those. Yes, bacha.
Yes, sir.
Yes, sir. Hydrogen is in plasma state in sun. It's very easy for sun to fuse to hydrogen and get helium and stay happy always. It does not have to worry about an atom bomb being created on sun because there is no nuclear fission happening. Do you understand this? Yes or no?
Yes, sir.
Yes, sir. No, sir. Please write it, sir. And that is the reason why we don't have nuclear fusion happening here, sir. Have you noted this down, bacha?
1 minute, sir.
Okay, sir. I'll wait for you, sir. Don't worry, sir. Nuclear fission. Nuclear fusion. Nuclear fusion cannot happen on Earth. High temperature and high pressure, not possible. You're trying to create it, still not possible. The car which runs on hydrogen is possible because our transport minister arrived in the car and it looks very nice. I saw that car. It is quite aerodynamic and it looks very great and it is fuel. It's not on a battery. It's on a hydrogen. It's running on hydrogen. Wow, great. Have you done this? Yes or no?
Sir.
Yes, sir. Shall I move ahead to the last point of this chapter?
Okay, sir.
Okay, sir. Then, sir, nuclear fission produces atomic bomb. What does nuclear fusion produce? Hydrogen bomb.
Atomic bomb.
Hydrogen bomb is what nuclear fusion produces.
Ukraine versus Russia.
Yes, bacha?
Russia versus Ukraine.
No, they are not going to use hydrogen bomb. Don't worry. Hydrogen bomb is based on nuclear fusion and it produces much more energy than an atomic bomb. We are not able to harness that energy, but we can have this counterpart of atomic bomb, atom bomb in fission. The counterpart is hydrogen bomb. You can have a straightforward question which says hydrogen bomb is based on which principle? And then the correct answer is, it is based on nuclear fusion. Don't get confused between an atom bomb, and a hydrogen bomb. I hope you will not get confused. Yes or no? Yes, sir. Then, sir, we will move on to our question answer session, sir. Shall we move on, bacha?
Yes, sir.
Yes, sir. I hope you have done many of the questions, sir. But it's my job to cover everything in the thing. And remember, on this nuclear fission and nuclear fission, most of the questions will not be numerical based. It would be knowledge based. Shall I start?
Sir, we will.
The first one comes from AIMS 2003. Nuclear fusion is possible. As I told you, simple formula based questions. Give me the answer, sir.
Answer A.
Answer?
A.
Answer is A. Let me see. Only between lighter nuclei. Question number 42. That is the correct answer, my dear friends. Well done. Do we understand how questions are framed here?
Yes, sir.
Just a minute, sir. I'm having
Take
problem
some
with-
water, sir.
Yes, sir. I'll have some water, sir, but first I'll do my job, sir.
Okay,
I'll
sir.
show you the next question, sir. You will think about that question and I'll have some water. This
First
question
help me,
comes.
sir.
Oops, the question is not there. Let me. Still not there. Let me try to squeeze it in. Okay, it's in now. Okay, bacha. This one. As I told you, question will come straight away from the what we have done. And do you see this? Do you
Yes, sir.
remember this, bacha?
Option A, sir.
Yes. If you don't see that graph, you will not be able to give me the answer, bacha. Do we understand this?
Yes, sir.
And that is why everything that we do in a class is of prime importance. Okay, we got this?
Okay, sir.
Okay, sir. Then, sir. This question, sir. I'll try to cover everything that can come in your examination hall. So every type of question I will try to cover. And this is again the next one. Let's see who gives me this. Not a straightforward one. You've asked the same thing in a different way. Let's see who can give me the correct answer.
Answer D.
36. Answer is D. No, bacha. I mean, D and B are both similar, right? Yes.
Yes, sir.
Yes, sir. D is correct. B is also correct. I think there is a printing mistake somewhere. I can't make out where the printing mistake is. I think B and D both are correct. Do we understand this? Yes or no?
Yes, sir.
Good, sir. Well done, sir. I am very happy with your performance, sir.
Thank you, sir.
And sir, you see, sir, every year the question has come. This was from the year 2004 and 2005, we had 2 questions coming from this topic, 3 questions coming from this topic. So very important this topic is. You understand this? That was 2004, this is 2005. Do you understand this?
Yes, sir.
Next question, sir.
Okay.
Question number 37, sir. In a reaction, something is happening. What is this reaction? Fission or fusion? Huh?
Sir?
Is this fission or is this fusion?
It is fusion, sir.
Yes, it is fusion.
Fusion.
Yes. In the reaction, this, the binding energies of this are A, B, C. Then what is the energy release in this reaction? Just put everything together and you will have the answer. What is the answer, bacha? In terms of binding energies, they are talking. Don't worry, everything is same.
Option C.
Option C, C minus A minus B. Do you all agree on this? Can I have some raise hands from everyone in the class? Not everyone is raising hands. Girls have disappeared.
Sir.
We understand this? Good.
Yes, sir.
Raising hands is good. So I understand that we are in the class and we are not doing our own stuff in the class. See, this is 2005. See, 3 questions are coming in 2005. See, 3 questions came in 2005 and I'll show you all those 3. See.
Less than 1.
Let me read the question first, yeah. I think you have done this question before, then.
No, sir.
Okay, sir. In any fission process, the ratio of mass of the fission product divided by the mass of the parent should be less than 1. See, now you understand. Again, 2005. Second question in 2005. Do we understand how many times the question has come?
Yes, sir.
And how easy these questions are?
Yes, sir.
Look. The next question. And you look at the year. Same year. Can I have the answer for this one, please? Fission of nuclei is possible because the binding energy per nucleon decreases with mass number at low mass numbers, increases with mass number, decreases with mass number at high mass number, increases with mass number at high number. This is how they confuse you. But don't get confused. You have the answer. What is the answer? Fission we are talking about, not fusion. Same question can be made in fusion. Yes, bacha.
Answer B.
Answer B, increases with mass number at low mass. This is not fusion we are talking, bacha. This is fission we are talking about. Fission. Right hand side wala graph, binding energy में right hand side वाला, fusion is binding energy में left hand side वाला. So what is
Answer
the?
A, sir.
Yes sir.
A.
अरे fission cannot happen for low mass numbers यार. Fission only happens at
High mass number.
high mass number. Why are you stuck on A and B? A and B are for fusion. Do we understand this?
Okay, sir.
So what is the correct answer, sir?
C.
Huh?
C.
C is the correct answer, sir. Because with higher mass number, binding energy decreases, it becomes less stable, and that is why they break. Do we understand this?
Yes, sir.
Yes, sir. I am getting confused, sir. So what I'll do if I change this question from fission to fusion, the red one, now what is the answer?
Increases with mass number.
If this was red one, then the answer was B. Do we understand this, or it has gone above our head saying bye bye, I'm going. I will not
Yes.
stop. I'm going.
Yes, sir.
Don't wait for me. Okay. So well done. As you can see, this is a very favorite topic for your exams, and that is why we have spent so much time on this. Most of the questions are going to come from this part. Here it comes. Same year, second question. No, the next year. Next year. Next year. Next year. 2006. 2006. 2006. The binding energy of a deuteron is 2.2 mega electron volts, and that of helium is 28 mega electron volts. If two deuterons are fused to form one helium, what is the energy released? Can I have your answers, please? Anyone with an answer, bacha? No? Shall I help you out?
1 minute.
Shall I?
Minute, sir.
We have done this question before. You gave me the answer C minus A minus B. Do you remember that question? C minus A minus B. Or shall I show you that question? C minus A minus B. The energy released. Binding energy of the product minus binding energy of the reactants. Do we remember this?
Yes, sir.
Binding energy of the product is 28. 28 minus binding energy of the reactants. 2 deuterium. 28 minus 2.2 minus 2.2. And the answer is
25.8.
what is the answer? I'll give you a minute. Have you got the answer for this one?
Yes, sir.
What is the answer then?
A. 25.8.
2 neutrons are fused, not 1, 2. So the answer is 28 minus 2.2 minus 2.2. If you can't subtract 2.2 from 28, 2.2, 2 times from 28, I think you are in the wrong class. You should take 2 out of your class and you should be in class 1. Yes or no?
Yes, sir.
Yes, sir. So the answer now, sir, is how much, sir?
23.6.
23.6. If you have taken so much time to do this, I am very displeased.
For 1 neutron, it's come 2 point.
If you can't read the question, then you again take 2 out of your class and you come to class 1. Yes or no?
Okay.
Or maybe you take 1 out and you come in class 2. Whatever. You are not liable to be in class 12. Yes or no? If you can't read the question correctly. Yes or no?
Yes, sir.
Yes, sir. So, sir, you are still in class 12th. Please remember that. If you can't remember this, then you have a problem, my dear friend. And your problem now will start. I don't know whether you remember this formula. Okay, before going on to this formula, let me take you again to a question from 2006. As you can see, this is a very favorite topic of your aims, of your AIPMT, of your NEET comes, and that is why we have done it. The operation of a nuclear reactor is said to be critical if the what?
1.
Okay,
K is equals to 1.
Chalo, we understand this. Good. I will have to shout if you do stupid mistakes like this. I will have to shout. There's no way out. Rather than shout. Let's see if you remember this one. If the nuclei of aluminum 2713 has a molecular nuclear radii of 3.6 fermi-meter. TE, what is T? I think I don't know. TE 12552 would have its radius approximately as how much? Now you have to go back in the past and see how the radiuses are related. Is that so? Do we remember it, bacha? Or we have forgotten what we had done? You can go back to the past and see it. I will help you out in going to the past because I only have the time machine. And this is what we had seen. The radius of a nuclei is directly proportional to the mass number raised to the power 1/3. Yes or no?
Yes, sir.
So I can write R1 radius of 1 divided by R2 radius of 2 will be equal to A1 by A2 and the cube root of that thing. Yes or no?
Yes, sir.
Yes, sir. Then, sir, we have the answer, sir. Put the values, get the answer, stay happy. Can you do that for me now?
Yes, sir.
Okay, sir. Please, sir, do it, sir, for me, sir. One time, sir. I will be very glad, sir. Please, sir. Help me out, sir. I'm in a fix, sir. Please, sir. Do I have an answer, sir? The question is right here, sir. So I have to find the radius of TE, whatever is TE is. So what will I do? Shall I do it or you are going to do it? I give you one last chance for redemption.
Sir, we will do 7.
Yes, that's what I like. I'll give you a minute. So there would be question in the examination hall which would require some calculation. But there will be some questions which will be straightforward. Do that straightforward question quickly so that you can have some time on these questions. I'll give you a minute, 2 minutes. Shall I give you the answer?
Answer 6.
Answer is 6. So B, 45. B, that is correct. How did you get it, bacha?
Yes, sir.
It
R1
is-
by R2 is equals to A1.
So I just write radius of beryllium divided by the radius of aluminium would be equal to A of beryllium. What is the A of beryllium? 125. Do we understand this? Yes or no?
Yes, sir.
Divided by A of aluminium. I am not visible, so let me come visible. A of aluminium is 27 raised to the power 1 by 3. Now what you have to understand, don't divide it first. First take the cube root. We understand this.
Sir.
So radius of beryllium divided by radius of aluminium is 125 ka cube root, which is 5. Yes or no?
Yes, sir.
27 ka cube root is 3. So
Yes,
I
sir.
have radius of beryllium, R of beryllium will be equal to radius of aluminium, which is 3.6 multiplied by 5 by 3. Do we understand this?
Yes, sir.
3.6 divided by 3 is 1.2. 1.2 multiplied by 5 is 6. The answer is 6 for me meter. Do we understand this? Can I have some raise hand from all of us in the class that we understand this and we are pretty happy about this? Okay. After this feast, let's have this question. Let us see how many of you can give me the answer for this one. Remember, nuclear physics is one of the hot topics. You expect questions from this. This relates to how beta particles are produced, and I hope you would be able to give me
Inside the nucleus. C, sir. Answer.
answer, sir. See, sir, and that is correct, sir. Thank you, sir. So do we understand this, bacha, everyone?
Sir.
One or two more questions before we wind off this chapter. The activity of a radioactive material is
Answer
simple. Ah, shabash. Well done. That is how you must be quick. That is how quick you must be to give the answer for the questions which are straight away theoretical. You cannot lose any time in this. Again, this one. The decay constant of a radiated sample is lambda. The respective value of its half-life and mean life are. First is half-life,
Answer
second
B.
one is answer B.
B,
Well done. Do you understand? Straightforward questions. You cannot take much time on that, because if you are taking much time on that, you will be losing a lot on the other questions which we cannot afford. This one.
Energy is released. B.
Yes, sir. See, sir. Questions are so simple, sir. You just keep faith, sir. You would be able to solve any question. See, I cannot solve all the 110 questions. I leave them to you, whatever are remaining. I am trying to solve all types of questions which covers the entire spectrum of the syllabus. I'm selecting questions on that criteria. Yes, bacha.
Energy equivalent to mass loss.
Energy equivalent to mass loss. So you understand the process? Yes or no? Mass defect, energy coming from mass defect is equal to mc square. We understand this? Yes or no?
Yes, sir.
Next question, sir. Based on concept, sir. Based on mass defect, sir. You got it, sir?
Mass of an alpha particle is.
An alpha particle has 4 nucleons, 2 protons, and 2 neutrons.
Less than. Answer is, sir.
Answer A, sir. We understand that, sir.
Yes, sir.
Then again, see, whatever we have discussed in the class, same questions have come. Nuclear fission is explained
Liquid
by.
drop model.
Now, so name is important. Do you understand this? The importance of knowing the fact
Yes, sir.
has come. That is why we have done this. So there is a reason why we do everything, that we understand this, yes or no?
Yes, sir.
Again, 2 more questions based on pure knowledge. I will show them together.
A, sir. Han and Strassman.
Who discovered nuclear fission? Hahn and Strassman. Who created the first reactor for me? We got this.
Yes, sir. D2O. Heavy water. D2O.
So you must remember the facts. I can't change the facts. I can't change the facts. I'm trying to cover all types of questions that are possible. I think we are almost done and we will finish with the last question, the most recent one. And as you can see, same question has come before. Yes or no?
Yes, sir.
Yes or no, sir? Same question, same data. Yes or no?
Yes, sir.
See, to do this question, maybe the same question comes in the next paper. You already know the answer. Yes or no?
Yes, sir.
Answer is D. Yes or no?
Yes, sir.
See, sir.
1. 3/5. Or 5/3. Yes, sir.
अरे अभी किया यार सर.
Yes, sir. Yes, sir.
Yes sir or no sir?
Yes, sir. Yes, sir. ऊपर नीचे हो गया.
ऊपर नीचे हो गया. ऊपर नीचे में 5 नंबर गया बेटा. ऊपर नीचे नहीं होना चाहिए. Okay?
Okay. Okay.
So we end this class here. We end this topic here. We are done with this topic. Next class we'll start with some more interesting topics. I'll share the sheet with you.
Topic. Next chapter.
I'll think about it. What we should cover. Okay. It again depends on which topic I think is more beneficial, is more liable to come. So I'll let you know. Okay. It may be semiconductors. It may be anything else. It may be communication system. For communication system, I might take only one class and I will tell you what all things you have to do and you'll have to study on their own, because there's nothing I'm going to teach as such there. So I'll see which is more productive and I will try to cover it in the next class.
Okay, sir.
Binding of
send sheet, sir.
Yes, I'll send the sheet. Don't worry.
Okay.
Chalo.
Okay, sir.
On that note, I'll wind up today's class. I hope you enjoyed it. Come tomorrow, and we shall have some new topics. Take care. Do the remaining of the questions on your own. They are straightforward ones.
Okay, sir. Take care.
Take care. Bye, beta.